the two modules I have there, flashcards. I'm going to make, they're not flashcards, they're written subjects. So I'm going to make a shit ton of flashcards.
Which one do you pick and the jumper
And bubbles. Bubbles and scratches.
What would you?
The financial models. Is that one math C or? Yeah, I'm pretty sure.
Okay, so we spoke about the diamond model yesterday, and two people not here. Two others who were here aren't here today. But the one thing that I didn't say right at the end, which is important, is we did say that you need the non-pecuniary cost in order to for the incentive structure to work, and there are critiques as to what this means. More importantly, in some ways, these are IID shocks across firms, and the non-pecuniary cost in itself has to fluctuate across realizations. And there really isn't a good reason for saying that in the real world, even if you think about that as costs that show up on the balance sheet of the firm, those costs actually fluctuate depending on what's happening. Okay, so that's another critique. But anyway, it's a theoretical study, and a nice one in terms of what we choose. So what we want to do today is go to our last model, in some sense a very important piece of work, and as often happens with these sorts of things, this is a paper that has a very large number of citations, and yet, apart from some technical nitty-gritty, there really isn't much work that has tried to extend it, see how it works in the more problematic cases that one can think about it. And that reflects the fact that doing those sorts of analyses is actually very demanding. It's a very nice piece of work. So it's the Diamond Lipig model. If I'm not mistaken, from the Journal of Political Economy. Together with Bernanke, they were awarded the Nobel Prize for this 2 or 3 years ago. I think. And and Dilbig were both doctoral students at Yale. When they started this work, Diamond was always trained as an economist at Brown and then Yale, and then he spent the rest of his life still in Chicago. Dilbig, on the other hand, was a physicist by training. And after that, he decided to finance, and he started working with someone called Steve Ross. And he moved with Ross, if I'm not mistaken, from Wharton to Yale. He had a phenomenal career. He had a job at Yale, and then shortly thereafter he moved back to the Midwest where he's from, as a very senior professor. You can look him up on the web, probably find it a bit strange. You know, it looks nothing like what we might expect a professor to look like. It looks like someone who plays, he probably does, in a folk rock band. And his work is very different. And yet, I'm very certain that much of what is demanding in this paper was done by Dilbig. So what's the story? The story is, what we saw yesterday is, we said, look, banks exist to provide a service, otherwise why would they exist? And that service is intermediation. So there are people who have funds available, they are the lenders in the economy, and there are people who need funds, they're the borrowers, the firms. However, the use that the firms put those funds to leads to a return which is risky. Not just risky, you need to pay in some ways in order to know what the return is. And for each individual lender to make that payment is too costly. And therefore, you have organizations called banks which pool together the resources of the lenders, and then they monitor the firms on their behalf. And then you need to think about, well, why won't the bank lie? The answer is the bank would lie if it could. And what we saw yesterday shows you how you get around that problem. Now, what we want to look at today is a different aspect of banking, which is that with banking, the key issue, of course, is if you think about running a bank yourself, you realize the problem is, it's all well and good to say that I'll pay a little bit of interest to collect resources, sink it somewhere else at a higher return, and make pots of money. That's fine. The problem is the people who deposited the money with you might at some point decide to ask for it. And there, of course, is a contractual relationship. And the contract specifies when you can, you cannot do such things. The problem is you might have situations where all of a sudden lots of people show up asking for their funds. So what banks typically do, some of it is regulated now, but even otherwise, they keep some of their funds in reserves. So a fractional reserve bank. Again, you know, macro classes, you might have heard the money multiplier and this and that, etc. All that's related to fractional reserve banking. We don't want to get into that. The point is, as soon as you have fractional reserve banking, what we observe is that historically, that has led to situations where all of a sudden you have bank runs, which is lots of people show up at the bank asking for their money back. The bank can't do that, shuts the window, and as a result, there's panic, and this happens across many banks at the same time. It's a systemic problem. Okay? So far, this is a story that you could tell in any class in economics, history or whatever, and give 300 examples, and everybody's happy. But that's not what we want to do here. What we want is a model of banking where bank runs are possible. We want to ask, is it the case that bank runs will necessarily happen? Is it the case that you can do something about it, and so what? Okay, and relate that to policies. And we see, of course, as always, there are things that don't quite fit in from the theory to reality, and what the data says. Okay. So what's the model? Now, I should say that there are two parts to the presentation here. At some point, I'll move to discussing the paper in detail, and you are required to read the paper. It's not as though I'm going to ask you what's in footnote 13. That's not the purpose. The purpose is to make sure that you read at least one really good paper in economics, which is accessible. Accessible in the sense not just that it's available to use for the VLE, but that you can actually read it and make sense of it. But I will go through the stuff in detail. Please do not try to, if you have any questions at all, there's always come and speak to me. Do not look at something on the web which tells you this is a simple way of understanding the diamond wheel. There's no simple way to do it. It's not a very complicated thing, but you need to do it here. Okay? Now, there is also an earlier part that I will be covering, which is not covered in as much detail in the paper, which is from a book, And that reading is available on the web, through the BLE. But I will cover it on the board, and you have it in the note. That builds up the bond market aspect of the problem, which I think is a nice thing to do. So what's the model? So there is one good. This is a partial equilibrium model, of course. I will not be writing everything on the board because you have the notes with you. But I will write a few things. 3 dates. Okay. 0, 1, 2. Okay. All these markets open for trade. And you will see that nothing will happen there. You'll see that in a moment. We also need to say what markets will come in. And here we have early consumption and then late consumption. It's later in just a moment. Okay. The idea is you have a whole bunch of agents, and later you will understand what a whole bunch is. For the moment, think of it as many agents. Many X and A. So at date 0, everybody looks exactly the same. Okay? So at date 0, clearly nobody's going to trade. Right? Why? Because given your environment, everybody faces the same environment, you will all wish to make the same trades, and therefore the aggregate trade will be 0 and the individual trade will also be 0. This should be clear. Right? However, at date 1, people figured out whether they are the early type or the late type. The point is that agents will be either of the early type or the late type, which is to say they will either wish to consume at 1 or wait and consume at 2. If they consume at 2, then they get no utility for consuming at 1. Is that okay? That's IID, and that's private information. Okay? So, type is IID and non-contracted, so it's private information. Okay, so far? Yeah? Maybe I should write here. Type is IID, private information, revealed. Okay, determined. I say revealed, you would want to reveal to whom? So it's revealed only to the agent, determined. So T equals 1, the agent knows. This is our own type. Okay. Preferences are very simple expected utility. Pi 1 u C1 plus a discount factor pi 2 u C2. These are probabilities, so they add up to 1. Rho is between 0 and 1. And your utility function is increasing and strictly concave. So there is risk aversion. That will be very important. Okay, so our risk utility model. And the endowment of each agent is 1. So what can the agents do? You have two technologies. There is a storage technology. So you put in 1 unit at time equals 0, and you get it back at time equals 1, here time equals 2, whatever you want. I'm writing in a storage 1 more. And there is a long-term technology. Where 1 is invested at t equals 0, and here, for the moment, we are going to make the realistic assumption that if you wish to liquidate at date t equals 1, you might lose a little bit. But later we will assume, as in the paper, that L is actually 1. So for the moment, we are alive to the possibility that there is some loss if you liquidate. there is a return larger than 1 if you allow it to mature. Right. So that's your structure support. So as we said, there will be no trade in the way things have been set up so far. However, the agent still has a decision to make in terms of how much to put into storage and how much to put into the long-term technology. Okay? So if I is the amount invested in long-run technology, then what you get at date 1, so if you turn out to be of the early type, you will liquidate because there is no point in you carrying that over to the next period. You're dead at that stage. So you get Li plus whatever you put into storage, which is 1 minus I. This is for the early type. And C2 will be R times I plus 1 minus I. So, okay. Now let's just think a little bit about this particular decision where we start. Okay, so your problem here is to maximize by choosing I, which has to be between 0 and 1. Okay. You substitute in from your, you can think of these as budget constraints. They're not quite budget constraints, but constraints which specify your consumption. So you get phi 1 u of C1 is Li minus 1, sorry, plus 1 minus I, plus rho phi 2, which is 1 minus phi 1, let's write it as phi 2, u of Ri minus plus 1 minus I. Okay, and let's take the derivative of that. Call it f, evaluated at I. That will give you, there you get L minus 1 by 1 u prime Li plus 1 minus I plus R minus 1 by 2 rho u prime I plus 1 minus I. Okay. And from the derivative, you should realize that your decisions will be the following. If the derivative at 0, right, is less than or equal to 0, okay, then you wish to invest nothing, because that's the derivative. Sorry, not f prime, f. So if that derivative is less than or equal to 0, then even with 0 investment, you're basically losing. But that can happen. If, on the other hand, you can find an I star at which the derivative is 0, okay, then you have an interior. But actually, it could even be at 0. Okay, solution. And similarly, you could have f of 1 is greater than or equal to 0. Okay, in which case I star equals 1. So all these possibilities are there since we have not imposed any boundary conditions. Since the our only conditions on U are that it's increasing in concave, strictly concave. This will give you just, yeah.
What would it mean when we say max and then we have the 0 less than or equal to I,
Yeah.
less than or equal to I
Yeah.
twice?
Sorry, this is 1. Thank you. All right. And you can check. So the check will be the formal thing to do. But notice over here, if L equals 1, then you would always put everything into the long-run technology, because you don't lose anything. Right? So you can check it from the first order condition for yourselves. Check equals 1, then I star equals 1, and therefore C1 star equals 1, C2 star equals R. So if there is no liquidity, no liquidation cost, then in fact your consumption is 1 and 1. Now, suppose we introduce, over here markets were at date t equals 0. Suppose we introduce a bond market at t equals 1. Okay, so this is all the boring stuff of the model in some ways, but it's a good exercise in everything that you've learned so far. Then we'll get to what these guys actually do, which is much more interesting. So suppose there is a bond market which opens at t equals 1, which is to say after you know your type. Right? So if you are the early type, you know that you've put something into the long-term technology which will pay off tomorrow. At which point you're dead. So what do you want to do? So you want to trade in such a manner that you get paid in order to transfer the rights to that return to somebody who is of the late type. Is that okay? Clear? Yeah? Yeah. So you've invested I star and we'll give you a return at t equals 2, at which point you're not around. So what would you do? So what you would do is use the bond market to get paid today so that the rights to that return get transferred to somebody who will realize tomorrow.
And you get paid by the person who's alive tomorrow.
Yes?
Yeah.
Okay. So a bond is a price. Okay? So you will get price times the number of bonds that you sell. Because you'll be selling bonds. Right? So if you sell a bond, the person who buys it from you will be entitled to the return of the bond, and you know the return. Correct? So bond market, price, P, okay? And we figure out the price in just a moment. Let's leave it as P at the moment. Okay, so early type sells how many bonds? Right? He will sell RI bonds. Sells RI bonds because that's the return that he will get from his investment. He sells RI bonds, and I'll put a star here, sells RI bonds, collects PRI, so that's the payment for the bonds that he's selling at T equals 1. Right? And therefore demand, demand, from the early type is minus RI because he's selling bonds. What about the late type? So the late type wants to sell the rights to the payoff that the late type would receive at t equals 1. Right? Because 1 minus I was invested in storage. Okay? So the late type sells payoff. Okay. this is, it's 1 minus I. Equals 1, okay? At price P, hence 1 minus I divided by P units of bond. Demand. Okay. So, now, price of the bond will be 1 over R. The reason is your safe technology gives you R units. The idea is you need to put it in at date 0. Okay? You don't liquidate at 1, and then at 2 it gives you R units. So anything that's already in that form at date 1, from there you're looking at what happens. This is part that's a bit not clear. Okay? But it would have to be priced off the technology, and therefore your 1 unit will give you R, and therefore the price of any bond which gives you 1 unit at t equals 2, that price would be 1 over R. Okay, so that's the price of the bond. And therefore, total bond demand and this is something that we will need crucial later. So the idea being, you have lots of agents, they all face the same probability with which they're early types and late types. The assumption that we are making, and this really is an assumption because the maths in this area does not let you show this. Okay? The law of large numbers, the way you've seen it, always says, for example, you take a coin flip. Okay? You get either a head or a tail. Right? If you flip the coin repeatedly, as the number of repetitions goes to infinity, as n goes to infinity, the sample average, so if the head counts for 1 and tails counts for 0, then the average will converge to the probability of the head. That's what the law of large numbers tells you. Right? Over here, if you try to do anything like that, you're talking about an economy with a countable infinity of people, which brings all sorts of problems with the maths when we do the economics. So the way we model this in economics is to say that 0, 1 interval is the set of your agents. Every point that's a real number between 0 and 1 is an economic agent. You have to accept what I'm saying and just say it will be fine. We would like to say that in such an economy, if each agent, 1 at each point in the real line, were to turn out to be of the late type or early type, you are able to say that there is a nice result, that on just about every realization, the fraction who turn out of the early type is pi 1, because pi 1 is the probability of being the early type. But there is no such result in maths, and it cannot be proven. This bit that takes 2 minutes is something that is usually not going to be told to you in any paper or any class that you take as an undergraduate. But I think it's important that you just know it, that there are lots of work, lots of papers in economics where this assumption is actually made. But they have to make the assumption. They might claim that it can be done, but it's well known for at least 80 years in the maths literature that this is a problem that is pathological and therefore badly behaved. Okay, so we need that. So we just have to assume it. And therefore, the total bond demand here will be, well, there's a fraction pi 1 of the agents who are the early type, each of whom demands minus Ri. And then there is 1 minus pi 1, a fraction of those agents who are of the late type, whose demand will be 1 minus I divided by P, but P equals 1 over R, so I can write that as multiplied by R. So that's your total bond demand. Okay? Equals 0 at equilibrium, and that tells you that I star is 1 minus pi. Okay, so now we are not looking at the autarky case. You're saying if there is a bond market, then in fact you look at things quite differently. Yeah. You're solving it in 2 stages. You're saying suppose you know what each agent, they're all identical to begin with, how much they all invested, and then you know that means that this is what their bond demand would be, but the bond market has to clear, and that gives you the value that you need for I star. All right? So it's a different way of solving the problem here, because of course the problem itself is different. So, equilibrium is specified by saying P star equals 1 over R. C1 star is P star Ri star. That's the early type who collects P or I, as we said earlier. But I is I star now, so it's P star or I star, plus whatever the early type had in storage. And that works out to 1 here, because P star R is 1. And C2 star is equal to R I star, which is their return from the long-term technology, plus whatever they collect by selling, right, there. Rights to the return from storage at date 1, and that works out to be R. And now notice you get 1 and R there, you get 1 and R here, but you got 1 and R here provided L was equal to 1. So when L is not equal to 1, the two solutions need not be the same. The bond market actually has a role to play when L is less than 1. Yeah.
Should that be 1 minus I star over pi star?
P star here. Okay. Is that all right? So far? So this is showing you what the bond market looks like. So now we get to the part of the paper. Let me write it over here. Now think about planners, bro. Just suppose the planner really knew who each person is. Let's make it simple to begin with. As we'll see later, there are only special situations in which we can work out solution when the planner does not know that. And those are the situations that we will be restricted to get to. First, let's think about what the planner would do in a situation where the planner knows people's types. Okay, so a fraction pi 1 will be of the early type. Okay, so the planner might as well maximize expected utility here. This is the X and A problem. So the planner knows that later there will be no issue with who is of what type, because they cannot lie since the planner knows the type. Okay, but to begin with, the planner will maximize U pi 1 UC1 plus rho pi 2 UC2, choosing C1, C2, and I, and the constraint here is important. Since everybody is identical, and by this incorrect law of large numbers, a fraction pi1 will turn out to be of the early type, right? Your constraint will be that a fraction pi1 will get C1, and that will be funded out of, so in per capita terms, the amount you put into storage is 1 minus I. That will be used to fund the consumption of the early types. And the rest will collect C2 at date 2. Is it okay? And therefore, our problem is to execute and then solve by choosing I, which will have to satisfy the inequalities which I'm not writing out. Okay, we will have interior solutions. So pi1 u of C1 will be 1 minus I divided by pi1 plus rho by 2 u or I divided by 2. First order condition. So the first order condition here will be, so pi1 u prime 1 minus I divided by pi1 minus 1 over pi1 by the chain rule plus rho pi2 Ri divided by pi2, sorry, u prime here. And then you get R divided by pi 2. You will set this equal to 0, and the value at which you can solve the equation is the solution. All well? Yeah? So of course, you can simplify this a little bit, and you get this simple first order condition, u prime 1 minus I star over pi 1 equals rho times R u prime R I star divided by pi 2, where you know pi 2 is 1 minus pi 1. Okay? Nothing very mysterious so far. Observe, and this is obviously going to be very special, if for some strange reason, let's say if you get very lucky, if u prime 1 equals rho R, u prime R, then I star equals pi 2. You can see that from there. Right? You get 1 there, and you will get R here, provided I star equals pi 2. If I star equals pi 2, then 1 minus pi 2 divided by pi 1 will be 1. That is asleep. Why are we interested in this? Well, that was the bond market solution. I star was 1 minus pi 1, which is pi 2. So you get the bond market solution in the planar solution only in a very special situation. Is that okay? But in terms of welfare, optimality, it's the planar solution that we get. In other words, this is showing you that in general, the bond market solution will not be great optimal. That's not what the planner would have done. That's the lesson so far. Is it okay? Questions so far? Anything at all that is not clear? Anything that you want me to clarify? We started on what's in the paper. And now things will start getting interesting. But we need to make sure that we've understood things so far. All well? Yeah? Okay, so now. We're talking about a planner. It's completely clear that there is no reason for the planner to know your type. So we need to think about when is it the case that you will get the same solution when the planner does not know your type. Okay? So we go to the important concept of self-selection. There's a huge area in economics on the economics of incentives, asymmetric influence. But a lot of it has to do with when do you get self-selection. You get around this problem by saying you set things up in such a manner that somebody has an incentive not to lie. They will actually be truthful. So that's the solution that we want. I star should satisfy that condition. And we want to know when is it going to be the case that people will not lie. Now think about the agents that we have. You have the early time and the late time. Right? So, let's reverse what you actually have in the notes. Flip it over. Let's ask first, will the early type ever lie and claim to be of the late type? Ask yourself, you're the early type, right? The planner tells you that you have some value for your consumption, and if instead you claim to be the late type, you have some other value for your consumption. Will you ever tell the planner that I'm of the late type? You see, late type gets more. You're the early type.
The population is,
Exactly what we have so far, the same model. Nothing's changed, right? You either get a third of an apple, or you can claim to be the late type, and you will get 2/3 of an apple. But when will you get it? Yes. At which point you're dead. Right? So one part of the problem is trivial because of the structure of the model. The early type will never misrepresent. Is this clear? So, there's basically no maths in this. It's just math. I mean logic. If you call that maths, that's fine, but you should. So the early type will never misrepresent because of the structure of the model. This is important. What about the late type? So now, what about the late type? Will the late type potentially misrepresent?
yeah.
Yes.
Why? And what will the late type get?
They'll get C1.
And what will they do with it?
Reinvest it to consume again.
Can't reinvest it. Okay? But you can save. That reinvestment bit we spoke about when we were talking about bonds. We didn't quite say that. We said it's already in the technology. Okay? So yes, so the late type misrepresents if and only if C1 star exceeds C2 star. Okay? Correct? And now, U1 C1 star, this is from the planar solution, equals rho R prime C2 star. It's a since. And your utility function is strictly concave. Right? So C1 star larger than C2 star tells you U prime at C1 star, you know, will be smaller than U prime C2 star. Correct? By concavity. When will that be compatible with the planar solution? It has to do with the factor rho R. Okay? Right? So, he will misrepresent if and only if C1 star is less than C2 star. By concavity of the utility function, that is equivalent to saying that, okay, I can write it here. By concavity of the utility function, if C1 star exceeds C2 star, then U prime C1 star will be less than U prime C2 star. Okay? So to get an equality here, rho R will have to be less than 1. Otherwise, you can't get it. You agree? Is that okay? Yeah. If and only if, since you print, right? Can happen only if. Happens only if. So from now on, we are going to assume rho R exceeds 1. So that C1 star less than C2 star and no one. This represents. Is that okay? Make sure that you understand this.
So we're essentially assuming that consuming later is more beneficial.
No.
Or
Careful. What we are saying is the assumption is rho times R exceeds 1. So you are not discounting too much. You know that R exceeds 1. That's the specification of the model. The technology is productive. R is larger than 1. You want to make sure that you don't discount too much. So that rho times R is also larger than 1. Because if rho times R is larger than 1, then from the first order condition, you know directly that the early type will be assigned less than the late type by the plan.
So it's like, okay, if you had an interest rate,
Yeah.
2%, but then your inflation was 3%, rho times R would be less than 1, and then you'd have people buying to consume.
You have to work that out, sort of along those lines. So you have to convert the inflation rate into a discount factor.
Yeah, exactly.
Correct. You can think of it in those terms, but I would encourage you not. I would encourage you to think directly, instead of doing it in terms of asset pricing, etc. I would encourage you to think directly in terms of this first order condition, also the asset pricing first order condition, but think directly in terms of that, and understand that rho R larger than 1 is what you need. Not just what you need, but that will give you exactly what you want. Is it okay? Yeah? Very good. We will make one further assumption. Taking up a lot of time. But so, assume, I'm writing this once again, rho R larger than 1, and there is this assumption on the curvature of the utility function. So this is the Arrow-Pratt measure of relative risk aversion, and you want that to be larger than or equal to 1. Okay? Because that ensures that you also have risk shared. So that in the Planner's solution, C1 star is strictly larger than 1, is strictly less than C2 star, which is strictly less than 1. So the Planner's solution provides risk sharing. You need that additional condition. Need. It's a sufficient condition. Okay? And this you will check on the problem set for the particular case of constant relative risk. Not the date. Okay so far? All well? So now the question is, well, that's the planner. The planner can go home happy and say, all right, that's done. I have a way of solving the problem here. There's no planner in the economy. What you actually see are bank demand deposit contracts. That's what banks offer. Right? The idea is we have to formalize what this means, okay? Which is a good part of what the paper actually does. That's the really key part, and then studying it. The point is, what banks, whenever you open a bank account, you actually have, I mean, nowadays you do this each time you open an account, which means all the time they use anything on the web. Right? You always have terms and conditions which you sign up to. Not a fine print as we used to call it, but nowadays it's just the font size, which nobody reads. But the fine print tells you what will happen in various contingencies. And in this case, what a demand deposit contract does, it says, okay, fine, you're going to put in 1 unit, say. What you get back will depend on what's happening. What does that mean? So, in some sense, if you were to speak to a bank representative, they would say, oh, don't worry about it, in general, you get your money back. And you ask them, when do I not get my money back? Okay, they will have to check. They come back and tell you, okay, so if this happens, if that happens, you won't get your money. What's the idea? The idea is the contract will specify a certain repayment if you go to the bank and if you are not too late. Okay? If you are late in the sense that a certain proportion of people have already approached the bank, then the window shuts. And you don't get back the promised payment. This is for the early types. A bank run always is about people rushing to the bank. What will the late types get? The late types will get what's left over after everybody who wants to take an action at date 1 has taken their actions. Okay? Depending upon what's left, that will get split up proportionately across the ones who haven't withdrawn. Yes?
No, it's just wondering if that would be nothing or.
It could be nothing, of course. That's the whole point. That's exactly the point.
Yeah.
So what we are going to show, I've run out of time today, I wanted to do a little more, but I've spent a bit of time doing this slowly. I think it's worth it. So hopefully we'll be able to cover everything on Thursday, we try. Otherwise, we can put in the arrangements for Friday. The idea being, we will first specify what diamond and delivery mean by a demand deposit contract with sequential service. Sequential service is important. So the idea is, although you have a continuum of agents, you think of them as lining up in front of the bank. And you